The next issue that we're going to address is sample size and power. And of course, those two go hand in hand. Let's think first about the factors that affect precision in a parallel group randomized trial. I showed you this formula earlier, or a variation on this formula. The variance of a condition mean, and that's y bar sub c, is the usual variance for a condition mean, sigma squared y, the variance of the outcome variable, divided by the number of contributions to the mean, and m is the number of members in each group, and g is the number of groups in each condition. So mg is the number of observations contributing to the mean. That's the usual variance of a condition mean. But because it's a group randomized trial, we have this variance inflation factor, the parenthetical piece, 1 plus n minus 1 times the ICC. And if you look at that equation, you pretty quickly will see what the factors are that influence precision. G is going to be very important. It appears in the denominator. So a bigger G is a good idea. M is in the denominator, but it's also in the numerator. So changing M is not going to help as much as changing G. The ICC is in the numerator, so smaller ICC is a good idea. And of course, the variance is in the numerator, so anything that you can do to shrink the variance is a good idea. We'll talk about these things in a little bit more detail as we go along. So this is the first of 3 figures that I'm going to show you. On the y-axis is the detectable difference in standard deviation units. On the x-axis is the number of members in each of the groups in our parallel group randomized trial. And the lines are distinguished by the number of groups randomized to each condition. The red line at the top, there are just 2 groups in each study arm. The black line at the bottom, there are 32 groups in each study arm. This particular slide is for an interclass correlation of 0.1, which in my experience is pretty large. We see that if we're looking at dietary intake in school children, where they mostly eat the same lunch at school. We'll see numbers like that in spouse pair data. We don't usually see interclass correlations that large for other kinds of measures that we see in group randomized trials in public health and medicine. So this is on the upper end of the scale. The thing to notice here is that if you've got only 2 groups in each study arm, you need an intervention effect of, 1.75 standard deviation units. And if you were sitting in front of me in a classroom, I would ask at this point, how many of you have ever had an intervention effect that large? And none of you would raise your hand, because it just doesn't happen. The intervention effects that we see in public health and medicine are in the 0.5 to 0.25 range, so the bottom part of the y-axis scale. And we get there if we have 16 or 32 groups per study arm, but not with 2 or 4. 8 is sort of marginal. So when the interclass correlation is large, we need a lot of groups in each study arm in order to have 80% power. The other thing that you'll notice is that adding members after you have about 100 doesn't really help much. Especially down towards in the lower lines, they're pretty flat after about 50. Even the upper line is pretty flat after about 100. So you get a lot more out of adding groups than you do out of adding members to each group. Now let's reduce the interclass correlation by an order of magnitude. So I'll back up. This was the original 0.1. Now 0.01. 0.01 is more typical of interclass correlations that we see in public health and medicine, and all of the lines dropped. We see a bigger gradient for adding members to each group, so we get some benefit out of it, even maybe up to 150. We still see good separation among the lines, so power is much better when we have more groups per condition. That's standard. But we can do pretty well with, we don't have to have 32. We can do well with 16. We can do pretty well with 8, maybe even 4 if we have enough participants in each group. So the situation is much improved when the interclass correlation is in the 0.01 range. And I'm going to drop it by another order of magnitude now. So have a mental image of this picture and then see what happens when I move to 0.001. The lines dropped again, and now we're in pretty good shape, except for the worst situation with just two groups per condition. Um, if we reduce the interclass correlation further, the lines don't shift very much. This is sort of the as good as it's going to get. And it demonstrates both the importance of the number of groups per condition. That is one very critical factor, and the other is the interclass correlation. You want a small interclass correlation if you can get it, and you want more groups per condition if you can get them. Power for parallel group randomized trials. You have to adapt the usual methods for power analysis to reflect the nested design. You've got the interclass correlation to deal with. You've got degrees of freedom based on the number of groups, not the number of people. I did a study was involved in the Minnesota Heart Health Program in the 1980s and 90s, and we had 6 communities that were assigned to study arms, 3 and 3 in each arm. We measured 20,000 people, but our degrees of freedom were 4 because we only had 6 communities. So you really need to think about how many groups that you've got. We've learned a lot since that early study. It's much easier now to find interclass correlation estimates. It's requested in the consort guidelines that studies report them, and many people do now. So if you're going to do a power calculation, you need an estimate of the variance of the outcome. You need an estimate of the interclass correlation. Power is more complicated for group randomized trials than RCTs. A very good resource is the one shown at the bottom of this slide, the NIH Research Methods Resources website. And I'm going to go to that a little bit later, and you can see some of the resources that are available there. What about IRGT trials? Well, power is even more complicated in an IRGT trial than it is in a parallel group randomized trial. Especially if you have a partially nested structure or a multiple membership model. So things can get complicated. Power is better for cross designs. The second best would be a partially nested design, and the fully nested design is the worst case for IRGT trials. They're very much in the same situation as a parallel group randomized trial. Here's a series of papers for methods for sample size estimation for IRGTs. The last one is one that I've mentioned several times already, Moyer et al. 2024. And you can use the same NIH website to do sample size calculations and learn more about doing sample size calculation for IRGT trials that we talked about a moment ago for GRTs. Step wedge designs, there are more correlations that we need to pay attention to. They're between period and within period interclass correlations. Those are both important. It's also important the number of groups that you've got, the number of steps, that is the number of time periods, and certainly the analytic method plays a role. So here are a number of papers presenting methods for sample size estimation in step wedge designs. And the NIH Research Methods Resources website is, again, a good place to go. If you've got an unbalanced design, that creates additional problems, and there's some references here. If the largest group is no larger than twice the size of the smallest group, you really don't have to worry about variability in group size. But if the variability is more than that, if it's 3 to 1 or 4 to 1 or 10 to 1 or 20 to 1, then you really need to pay attention to the imbalance. It's going to hurt power in the sample size calculation and the analysis, and it can actually inflate the type 1 error rate if you ignore it in the analysis. So it's an important issue. The Johnson et al. Paper in the middle of this list, 2015, is particularly good on talking about the type 1 error rate. A number of these papers are good in terms of talking about power. So let's talk a little bit more about resources that NIH provides publicly available. Encourage you to use them. There's a 7-part online course on group randomized trials and IRGTs. We, about once a month, have a Mind the Gap webinar. We have one coming up at the end of September 2024 on what to do with variable cluster size in a parallel group randomized trial. So the topic that we were just talking about, if you have imbalance in the size of the clusters, that's going to be the topic of one of our Mind the Gap webinars. And they're all recorded and available online, and you can look at them. The other resource that I think is particularly important is the Research Methods Resources website. In the early days when I was talking about this material at the Summer Institute, we didn't have this website, and I couldn't point people to it. And I was trying to help them learn how to do sample size calculators with a spreadsheet on a laptop. This is much easier. This is what it looks like if you go to the Research Methods Resources website, and if you click on sample size calculators, the calculators tab, you'll land on this page, and there's a little general information on sample size calculation. There is a separate calculator for each of 4 designs that we deal with on this website. The parallel group randomized trial, the individually randomized group treatment trial, the step wedge group randomized trial, and there's a 4th one, which I haven't talked about today, a group-based regression discontinuity design. So we have a calculator for that design as well. We'll talk about that in the 4th segment. So if you opened up the sample size calculator for parallel group randomized trials, you'll see that there are 9 steps that you need to go through. There is a lot of text available. It's really a tutorial built into the sample size calculator. So if you clicked on more, you'd see information about type 1 and type 2 errors. And then you'd make your selection for the type 1 error rate and for power. And you'd click on through the various sections here, entering the information. Once you're done, and I'm going to skip past this for a second. Once you're done, you're going to get a page that looks like this, showing you the results. And it shows you groups per condition across the top, members per group as the row headings, and the cell in the center is the result, because apparently you specified 100 members per group, and the program calculated that you need 14 groups per condition for the effect size that you entered, in this case, 0.2411. And you get on the right a summary of the parameter estimates that you put into the expression. You can always go back once you've got that initial result to any of the steps and change any of the inputs, and then jump back down to analysis and press submit again, and it'll redo the calculation based on the new inputs. You can print those, you can save them, you can download them as Excel or Word documents or PDFs. So you can do a lot of what if experiments and see, well, what happens if I can shrink the interclass correlation? Or what happens if I add more groups or increase the number of members? Or what happens if I include regression adjustment for covariates? So there's a lot that you can learn by playing with the calculator, and each of the calculators is similar. This is for parallel group randomized trial, but if you were to look at the one for IRGTs or for step wedge, they look very much the same, with generally the same steps and the same kind of write-up. So if you use one, the others are going to seem to be familiar. Something else that we offer is worked examples. So you'll see at the top of the column of steps in light blue, it says View Worked Examples. If you click on that, it will take you to a section on worked examples, in this case for the parallel group randomized trial. And you can look at worked examples for detectable difference and for a variety of designs. So we have some for a simple difference. We have others for a net difference. So the simple difference is what you'd have if you're analyzing post-test adjusting for baseline, for example. The net difference is what you'd have if you're doing a repeated measures ANOVA or ANCOVA, for example. And we provide worked examples for cohort, for cross-section, for the net difference, and that doesn't matter for the simple difference. And if you clicked on any of those, you'd see a Word document that looks something like this, You'll see the formula that's being used to estimate the detectable difference and an explanation of all the terms. You'll see the parameter estimates that are being used, and you'll see the actual worked calculation. And this one was for the result that I showed a moment ago. The 0.2411 is the detectable difference that I entered. And if I have 14 groups and 100 members, that's what I have 80% power to get. And you can follow the logic as shown here. So these resources are publicly available. All you have to do is go to the links. You can play to your heart's content. Strongly recommend that you spend time on the Research Methods Resources website. We try to keep it up to date. It supports, for example, analytic models and sample size calculations for the step wedge design that reflect time varying intervention effects. It will soon, doesn't today, but it will soon, by the end of the year, reflect Moyer et al. 2024, that new work on individually randomized group treatment trials. So we do try to keep it up to date. And in summary, for this section, I would note that the parallel group randomized trial is the best design if you've got an intervention that operates at a group level or manipulates the social and physical environment or can't be delivered to individual participants without substantial risk of contamination. IRGTs are widely used, rarely recognized as such, often not analyzed correctly. So you all have been warned, don't do that. And step wedge designs can be somewhat more efficient than parallel group randomized trials. That's one of the reasons people like them, but they usually take longer and face more threats to internal validity. So I don't recommend them unless it's really important to do it. If you're new to these designs, find an experienced methodologist. Most universities have biostatisticians who are familiar with mixed models and can quickly get up to speed on the issues that I'm presenting here. So it's not hard to do anymore. And that wraps up our section on sample size and power. We'll turn next to alternative designs.